no asteroid, no supervolcano, no single catastrophic event. And yet, 34 million years ago, almost the entire mammal fauna of Europe was wiped out and replaced completely within a geological eye blink. What caused one of the most dramatic biological upheavals in the history of this planet? The answer involves a melting continent, a rising land bridge, and the most devastating invasion in the history of life on Earth. To understand what was lost, we must first understand what existed. The Eocene Epoch, spanning roughly 56 to 34 million years ago, was one of the warmest periods in Earth's history since the extinction of the dinosaurs. Global temperatures were significantly higher than today. There were no permanent polar ice caps. Sea levels were higher. The world's climate zones were compressed toward the poles, meaning that tropical and subtropical conditions extended far further from the equator than they do now. Europe, in the Middle and Late Eocene, was not the temperate peninsula we know today. It was an archipelago, a collection of large islands and connected land masses, partially separated from Asia by a shallow seaway called the Tethys Sea and its remnants. Dense tropical and subtropical forest covered most of its surface. The climate was warm and stable in a way that is difficult to fully imagine from the perspective of the present. And in these forests, across these islands, a unique mammal fauna had been evolving for millions of years in effective isolation. The Paleotheres were among the most characteristic animals of Eocene Europe. Superficially, they resembled horses, four-legged, hoofed, browsing herbivores. But they were not true horses. They were more closely related to tapirs, and they came in a remarkable range of sizes, from small dog-sized forms to animals approaching the bulk of a modern rhinoceros. They were the dominant large herbivores of the European Eocene, filling the ecological roles that deer and cattle fill today. In the trees lived the Adapid primates. These were genuine primates, relatives, however distant, of the lineage that would eventually produce humans. And they had been present in Europe since the early Eocene. They were roughly lemur-like in appearance, arboreal, fruit and leaf-eating, occupying the forest canopy of a continent that was warm enough to support them. The rodent fauna was entirely distinct from anything in Asia or North America, endemic lineages that had diversified across the European islands over millions of years, filling every available small mammal niche. The carnivore guild was occupied by the creodonts, an ancient group of carnivorous mammals not closely related to modern carnivorans that had been the dominant predators across much of the world since the early Paleocene. It was a complete, mature, highly structured ecological world. Strange to our eyes, none of these animals are familiar. None survive today, but internally coherent, stable, and by all indications, thriving. It was also, though no animal living in it could have known this, profoundly vulnerable. Its vulnerability lay in the very thing that had made it so rich, its dependence on warmth. Every animal in this ecosystem, from the Paleotheres browsing in the forest understory, to the Adapid primates in the canopy, to the rodents in the leaf litter, had evolved for a warm, stable, humid world. They had no experience of cold, no physiological adaptations for seasonal extremes, no behavioral toolkit for surviving in open, treeless landscapes. They were perfectly adapted to the world they lived in, and that world was about to end. The transition from the Eocene to the Oligocene epoch, approximately 34 million years ago, represents one of the most significant climatic shifts of the Cenozoic era, the geological period that began after the extinction of the dinosaurs and continues to the present day. The trigger was Antarctica. Throughout the Eocene, Antarctica had been ice-free. Forests grew there. The continent was cold by the standards of the tropics, but not frozen. This was possible because of the configuration of the southern continents. South America and Antarctica were still close enough together that warm ocean currents circulated around the southern polar region, preventing the deep cold from taking hold. As South America drifted northward and the gap between the two continents widened, a new ocean current became possible, what geologists now call the Antarctic circumpolar current. Cold water began circulating around Antarctica in an unbroken ring, isolating it thermally from the warmer waters to the north. Without the moderating influence of those warmer currents, Antarctica began to cool. Ice began to accumulate, and as the ice sheet grew, it reflected more sunlight back into space, cooling the planet further, a feedback loop that accelerated the process. The effects were global, and they were rapid by geological standards. Global average temperatures dropped by approximately 4 to 5 degrees Celsius over a geologically short interval. Sea levels fell as water became locked in the growing Antarctic ice sheet. The atmospheric circulation patterns that had kept Europe warm and humid began to shift. For Europe's tropical forests, this was catastrophic. The forests did not simply cool, they fragmented. As temperatures dropped and seasonal variation increased, the continuous canopy that had covered much of Europe began to break apart. Patches of forest became separated by open ground. River systems changed course. The shallow seaways that had partially isolated the European islands from each other shifted, sometimes connecting previously separate land masses, sometimes dividing them. The animals living in these forests faced a compounding crisis. Their food sources were declining as the forests shrank. The stable temperatures they depended on were becoming unpredictable, and the fragmentation of their habitat was isolating populations from each other, reducing genetic diversity and limiting the ability to move toward more favorable conditions. The fossil record from this period in Europe shows a clear pattern of declining diversity before the Grande Coupure boundary itself is reached. The Paleotheres were already reducing in species richness. The adapid primates were retreating southward, following the warmth. The endemic rodent lineages were showing signs of stress. Europe's ancient fauna was already weakened, already diminished, already losing ground when the invasion began. The same falling sea levels that were disrupting Europe's ecosystems were, simultaneously, opening new geographical connections. For much of the Eocene, a shallow seaway had separated Europe from Asia along what is now roughly the Ural region, the remnant of the ancient Tethys Sea. This barrier had been critical in maintaining Europe's biological isolation. It was the reason European mammals had evolved so distinctly from those of Asia and North America. As long as it existed, the two faunas remained separate. As sea levels dropped in the early Oligocene, this barrier shrank. Land that had been submerged became exposed, a connection formed, and the mammals of Asia, which had been evolving in a very different kind of world, cooler, more seasonal, more open, found themselves with a route westward into an emptying continent. The Asian fauna that crossed into Europe was fundamentally different in character from what it was replacing. The perissodactyls arrived, the group that includes the ancestors of modern horses, rhinoceroses, and tapirs. True rhinoceros relatives appeared in Europe for the first time, stocky and adapted to more open environments than the Paleotheres they were replacing. These were animals built for a cooler, more variable world. The ruminants arrived, the group that would eventually produce deer, cattle, antelope, and giraffes. Their first appearance in the European fossil record coincides almost precisely with the Grande Coupure boundary. They brought with them a digestive adaptation. the ability to ferment plant material in a specialized stomach that made them far more efficient at extracting nutrition from the lower quality vegetation of cooler, more open landscapes. The rodents were replaced almost in their entirety. The endemic European rodent fauna, lineages that had been present for millions of years, was swept away and replaced by Asian forms so completely and so rapidly that paleontologists use the rodent assemblage as the primary tool for identifying the Grande Coupure boundary in the fossil record. If you are looking at European Eocene rodents in one layer and completely different Asian origin rodents in the next, you have found the boundary. New carnivore lineages arrived from Asia as well, ancestors of the true carnivorans, the group that includes modern cats, dogs, bears, and weasels. The ancient creodonts, which had been the dominant predators of the European Eocene, found themselves competing with more efficient hunters, better adapted to the changing conditions. The scale of the replacement was staggering. Studies of the fossil record across the Grande Coupure boundary show that in some European localities, the mammal fauna changed by over 80% at the genus level within what appears, in geological terms, to be a very short time interval. Animals that had been present for millions of years simply do not appear above the boundary. Animals that had never been seen in Europe appear for the first time. It was not a gradual transition. It was a break, a sharp, clean line in the rock, above which the old world no longer existed. Not everything disappeared at once. Some of the endemic European lineages persisted into the early Oligocene, surviving in the warmer refugia of southern Europe, the areas around what is now the Mediterranean, where temperatures remained slightly more tolerable. The Paleotheres held on longest in the south. Some species persisted for several million years into the Oligocene before finally going extinct, the last representatives of a lineage that had once dominated the continent. The fossil record preserves them in diminishing numbers, retreating southward, their range contracting, until eventually there are no more. The adapid primates similarly retreated toward the south and eventually disappeared from the European record entirely. Europe would not have primates again until humans arrived, tens of millions of years later. The creodonts lingered for a time, but they were competing now against carnivorans in an environment that increasingly favored the newcomers. By the mid-Oligocene, they too were gone from Europe. What the fossil record preserves in those final layers of the Eocene and earliest Oligocene is something that feels almost elegiac, a fauna in retreat. Animals that had been the masters of their world for millions of years, reduced to remnant populations in diminishing patches of suitable habitat, while around them a new world assembled itself from entirely different components. The old Europeans did not go quietly, but they went. The Europe that emerged from the Grande Coupure was a fundamentally different place. The climate continued to cool through the Oligocene. The tropical forests that had covered the continent in the Eocene gave way to more open woodland, grassland precursors, and seasonally variable landscapes. The shallow seaways that had fragmented Europe into islands mostly retreated, connecting previously separate land masses into a more continuous continental mass. And across this new landscape moved a new fauna, one that, while still alien by modern standards, contained the recognizable ancestors of animals we know today. The early rhinoceros relatives diversified into multiple ecological forms. Some became large browsers, some grazers. One lineage in Asia would eventually produce Paraceratherium, the largest land mammal that ever lived, though that story belongs to a different chapter. The ruminants began the adaptive radiation that would ultimately produce the extraordinary diversity of hoofed mammals alive today. from the small, generalized browsers that crossed into Europe at the Grande Coupure, evolution would eventually produce red deer and water buffalo, wildebeest and giraffe, domestic cattle and the wild sheep of the mountains. The carnivorans established themselves as the dominant predator guild across Europe and Asia. The lineages that crossed into Europe in the early Oligocene would give rise, over tens of millions of years, to the wolves, bears, lynxes, and otters of the modern European fauna. The rodents, the Asian forms that had so completely replaced the endemic European lineages, diversified rapidly into the ecological space available to them. Their descendants are the mice, voles, squirrels, and beavers of contemporary Europe. In the trees, fewer trees now, in a cooler and more open world, small, sharp-eyed mammals continued the quiet business of primate evolution. Not in Europe, where the primates had been extirpated, but in the warmer regions of Africa and Asia, the lineage continued. It had time. It had tens of millions of years still ahead of it. The Grande Coupure is not simply a historical curiosity. It is a case study in how biological communities respond to the simultaneous pressures of climate change and the introduction of new competitors. Europe's Eocene fauna did not go extinct because it was inferior. The Paleotheres were successful animals. The adapid primates were successful animals. The endemic rodent lineages had been thriving for millions of years. They went extinct because the world they had been built for stopped existing. And because, at precisely the moment of maximum vulnerability, a wave of animals arrived that had been built for the world that was replacing it. The timing was the critical factor. Had the climate cooled more gradually, the endemic fauna might have had time to adapt. Had the land bridge opened in a period of climatic stability, the endemic fauna might have been robust enough to compete. It was the combination, climate stress followed immediately by biological invasion, that produced the near-total replacement visible in the fossil record. This pattern, endemic fauna weakened by environmental disruption, then overwhelmed by invaders, has repeated itself throughout the history of life. It happened when North and South America connected 3 million years ago. It is happening today, as human activity both changes climates and moves species across geographical barriers that previously kept faunas separate. The Grande Coupure happened 34 million years ago. But the mechanism it illustrates is not historical. It is ongoing. The name is apt: the Great Break. In the geological record of European mammals there is a line. Below it, a world of Paleotheres and adapid primates, of endemic rodents and ancient creodonts, of animals found nowhere else on Earth, products of millions of years of island evolution in a warm and stable world. Above it, a different world entirely. Rhinoceros relatives and early ruminants, Asian rodents and ancestral carnivorans, the foundations of the modern European fauna, assembled almost overnight from components that had arrived from another continent. Between those two layers, a climate that collapsed, a sea barrier that fell, and a crossing that changed everything. No single catastrophe caused the Grande Coupure. No asteroid, no supervolcano, no sudden mass death. What caused it was slower and in some ways more relentless. A shift in ocean currents on the other side of the planet, a growing ice sheet on a continent most of the animals affected had never been anywhere near, and the consequent unraveling of the stable, warm world that 34 million years of evolution had built. The animals that disappeared were not failures. They were, in every meaningful sense, successes, until the criteria for success changed beneath them, and the animals that replaced them, The ancestors of the deer grazing in European forests today. The ancestors of the wolves that once hunted them. The ancestors of the mice in the walls of every house on the continent. They did not win because they were stronger or smarter or more deserving. They won because they arrived at the right moment, built for a world that was just beginning. 34 million years ago, Europe lost a world it had spent millions of years building, and began, without knowing it, building ours.